Hello and welcome to this webinar on predictive analytics for industrial IoT applications. My name's Craig Lawton. I'm an IoT specialist architect based out of Australia. Today we're going to do an overview of industrial IoT and the trends that we're seeing in the market. Then we're going to dive into some use cases where we're seeing customers build solutions for industrial IoT using our services. We're going to dive deep into a couple of architectures on predictive maintenance, and we're going to walk through a Jupyter notebook that looks at predictive maintenance for turbofans in aircraft. Then we're going to dive into another use case, which is predictive quality, and we're going to compare those architectures with the predictive maintenance, so you understand the AWS components that you can use to build these solutions. And at the end of the session, we've got about 15 minutes for Q&A, so start writing down those questions. Now, the Internet of Things has emerged from a convergence of many different trends. With the ubiquity of the Internet, the decreasing cost of connectivity and devices, and these devices becoming more powerful, industrial companies can create smarter machines. And with billions of devices becoming connected to the internet, and developers are working on more and more IoT applications, and analysts are predicting that the market is going to grow to $110 billion by 2020. Now, the goal of IoT is so that you can understand the state of your devices, so that you can build and improve on your current service and business models over time and improve your customers' experience. That's because using IoT means you can understand your operations better and make decisions quicker and make better decisions, or evidence-based decision making, as we like to say. For example, manufacturers can improve their processes and reduce costs and do things like increase the safety of their environment. And different countries are adapting different processes and standards that refer to this. It's commonly understood as the fourth industrial revolution. In Europe, it's referred to as Industry 4.0, and it's all about building a modular, structured, smart factories. Japan's taking a very holistic approach, which looks at integrating manufacturing into all levels of society. China referred to it as MIC 2025. Now, the vision behind all these initiatives, though, is similar. It's to build smarter factories that can move countries' manufacturing up the value chain, move away from deploying large amounts of CapEx to more of an OpEx model, make your industrial processes more flexible and adaptable so that you can customize solutions for your customers and operate at greater efficiencies. Now, the Internet of Things is continuing to evolve. Now, some interesting analyst points to note. Bain predicts B2B IoT segments will generate $300 billion annually by 2020, and that includes about $85 billion in the industrial sector. The Boston Consulting Group predicts the IoT market will reach $267 billion by 2020. And 50% of that's going to be driven by manufacturing, transport, and logistics. And in a recent article, Forbes reported that the IoT market is projected to grow to $662 billion by 2021, with many of them coming from IoT cloud opportunities. So it's a rapidly growing area. Now, when we speak to customers, they have common challenges and concerns when deploying these solutions. They're concerned about device security and how that impacts downtime and how to onboard things like legacy equipment. They're challenged by getting the right security policies in place. IoT fleets are diverse. There's a long lifetime for a lot of these devices, and there's legacy equipment. And in traditional environments for manufacturing, networks have been increasingly have been isolated from external networks. And to take advantage of cloud computing, you need to understand how to secure in more open networks. Downtime, of course, is a major concern. If operations are stalled or stopped, then revenue is going to be lost and their business impacts are immediate. And as I mentioned previously, there's a lot of legacy equipment out of there. Factories are traditionally deployed with decades-long life cycles, and there's millions of dollars of investment that need to be looked after at the same time as looking to adapt these new solutions. And in these brownfield environments, the type of things that we see in the operations environment, you see many different types of equipment, different types of protocols, industrial solutions built with PLCs and SCADA type solutions. They're operating out on the factory floor. Security is essential, and it needs to integrate with IoT through a number of firewalls for enterprise resource planning and those types of things. Some common industrial control standards that are understood are ISO 95 and ISO 99. Now, ISO 95 refers to integration standards and how you build these manufacturing IT solutions. And ISO 99 refers to the security of said solutions. And it's a multi-layer approach. Down at layer 0, you have the equipment, which is operating and actually performing the functions on the floor. They typically integrate with PLCs at level 1. Layer 2, you have things like SCADA systems. You've got a wide range of protocols like Modbus and OPC, and sometimes the SCADA protocols and devices at level 2 interact directly with level 0 as well. And those devices then need to integrate at layer 3 with the MES layer, which is understood as the manufacturing execution system. This MES layer at layer 3 is critical because it acts as the IT layer between these operational systems on the floor and the ERP systems. So in that place, we've in the diagram here, we've got AWS Greengrass. Now, we'll talk more about that later. That's our IoT Edge platform, which takes functions previously that were performed in the cloud and can still be performed in the cloud, but you can execute those functions now down in edge devices like industrial gateways and build things like protocol adapters and data aggregating solutions and those types of things at the edge. And then as we go up from layer 3 to layer 4 and 5, we move towards the enterprise resource planning systems, which give you more of a view of the whole enterprise, things like product lifecycle management and human resources management, those types of things. And they can typically be hosted in the cloud. As you can see, we've used MQTT for telemetry data. It's a very lightweight Internet of Things protocol, which is great for communicating lots of packets in a very power efficient way. But you also have options to communicate using HTTPS and other protocols upstream to the cloud. And some of the use cases that we see that we're helping our industrial customers overcome are in the realm of predictive maintenance, predictive quality and asset condition monitoring. We'll talk about the first two today. First, just to tell you a little bit about IoT, AWS IoT allows you to build in device authentication authorization, and this allows you to keep your IoT data and devices protected. That's how we build our services, security as job zero at AWS. Now, we provide the ability for you to continuously audit these security policies for your devices and look for things like abnormal behavior and receive alerts if something's not quite right. And you can take predictive action such as powering off the devices or pushing a security fix, for example. Secondly, with AWS IoT, it enables connected devices to operate with intermittent internet connectivity to mitigate the risks of unexpected downtime. Now, as I've noted, traditional brownfields environments have been used to operating for a long time in isolated networks. And so with our AWS IoT service, it allows you to build solutions which can run when you have a intermittent internet connectivity. And thirdly, AWS IoT lets you easily connect, manage and update devices, a wide range of devices from small microcontrollers to much more powerful devices like industrial gateways. And that allows you to integrate your existing legacy equipment such as PLCs and SCADA systems by deploying simple sensors to monitor processes and track key performance indicators without having to replace all the existing hardware. And AWS IoT allows you to scale very quickly. So you can build solutions that start small and scale to thousands or millions of devices and billions of messages. And we provide the capability for you to organize device inventory, do things like over-the-air updates, and index and bulk to provision your devices, for example. And once your devices are on the AWS IoT service, it's really easy then to use our analytics services to collect, process, and analyze that IoT data. And the great thing is that we've got services around machine learning, and you can look at trends in the data you're collecting from your IoT sensors and start to predict when things are going to fail. That's the predictive maintenance solution. And that's what we're going to dive into next. Now, at a high level, predictive maintenance makes use of some key services in our ecosystem. So you've got at the left there, you've got things like machines, cameras, and MES systems, which are generating lots and lots of data. As I mentioned previously, AWS Greengrass is available. It can be deployed out in edge devices in your facilities, and this can process the data and prepare it, normalize it, drop the data that isn't relevant, and do a whole lot of interesting things. That data then can be forwarded onto the AWS IoT core service in the cloud, and that allows you very easily to get that data into the cloud, and you can use the rules engine then to route those messages to a host of other AWS services. In this example, where we're selecting messages and sending it through to the AWS IoT Analytics service, which stores the data in a time series database. Now, you very quickly use our QuickSight service, which is our business analytics platform, to get visual dashboards on the data. So there's a tight integration between those services, and the QuickSight service is great for really quickly getting into these cloud-based data sources and creating great visual dashboards, etc. Now, the other thing that IoT Analytics integrates with is our SageMaker service. And as you can see in the diagram, the SageMaker service can access the IoT Analytics data that you're collecting. And you can use SageMaker service and a hosted Jupyter notebook within that to create machine learning models that can predict things like maintenance on devices. So you've got a system now where you're collecting the data into a cloud-based solution where you pay for what you use. It's in the analytics service, and then you can use our machine learning service, which is SageMaker, to build and train a model that can predict when devices are going to fail. Now, the great thing is that you need a lot of power and compute in the cloud to build these models, and it's a great place to store large data sets in the cloud. But once you've actually trained a model to predict when a device is going to need maintenance, that actual created model is actually a discrete bit of compute, and you can deploy that down to Greengrass. There is integration between SageMaker to take a trained machine learning model and deploy that down to run locally inside an industrial gateway in your facility. And that means that when you do the inference on when something needs maintenance, it's actually occurring in the facility. It doesn't require an internet connection, and you can have those alerts, if you like, provided locally to people on the factory floor. So there's many reasons that customers seek to do predictive maintenance solutions on AWS. Some of them are like to reduce costs, and of course there is a cost in creating work schedules to go in there and do maintenance. So if you can plan that maintenance work proactively, then you're going to be able to manage your costs better. And of course, unplanned production outages is an obvious one that you really don't want your plant going down. So customers are seeking to keep the manufacturing plant running as quickly as possible. A customer that's doing great work with us is called EMS, and they're using AWS IoT to detect fuel leaks early in petrol stations to minimize environmental impact. And they've delivered a 500% ROI using our services. And the quote from the founder and managing director was, "With our AWS IoT-enabled fuel suite solution, customers manage their petrol stations proactively rather than reactively to dramatically improve efficiencies and detect fuel leaks early to minimize environmental impacts." So it's, customers are building these solutions now on AWS, and it's great to hear their stories. And if we step through the process of creating these predictive maintenance solutions, at a high level, you ingest all this sensor data from devices in the plants and offsite, and you you securely then connect all that data from up to billions of devices into our AWS IoT core service. Now, we've got software like FreeRTOS and Greengrass, which will allow you to integrate with nearly any type of device at the edge. And we've also got the Device Defender service, which allows you to make sure that you're tracking anomalies or incorrect configuration or software deployments to devices. So you're making sure your entire environment's secure at all times. Now, that gets the data into the cloud. Once you're in the cloud, you want to use that data you collect over time to build these predictive models based on the data, based on what you've seen. Machine learning is great at inferring things from past data. Now, once you've built these models, you build them in the cloud because you need access to lots of compute power, and these data sets are quite large, so cloud's a great place to store them. But once you've created the model, you can then deploy the model to run locally. And so the predictive maintenance model is running potentially in your facility, looking at the live data that's coming in, and it's looking for those anomalies which are going to indicate that maintenance is going to be required. And that makes use of our IoT Analytics service in the cloud that stores and processes the data, but the prediction models you can deploy at the edge are predicted using our edge service, which is called AWS Greengrass. Now we'll jump into a predictive maintenance architecture that has been used by some of our customers. This is one before the IoT Analytics service was available. And if you have a look, you've got sensor data ingested at the top left there from factory machines. It's ingested for things like MES and SCADA systems. That data is then routed to a gateway running Greengrass. Now, as you can see, before it gets to Greengrass, there's a Lambda function that does protocol conversion from industrial protocols to standard internet protocols. Now, that Lambda function's running inside Greengrass. Now, Greengrass provides a local MQTT broker, so it can send messages to other devices at the edge, but it can also route messages up to the cloud. It's got a local certificate authority, so everything in that Greengrass environment can only talk to the devices which have mutually authenticated certificates using that local CA. So what that means is that devices as part of a Greengrass group can only talk to each other and to the cloud. It provides best of breed IoT security. Greengrass doesn't need much to run. It only needs 128 meg of RAM and one core CPU, so it can run on pretty much anything. And it's a great solution too, where machine data can't reach the cloud because of perhaps you need to act on it locally with low latency, or perhaps there's intermittent or constrained network connectivity and you want to keep some data locally. Now, Greengrass supports hybrid end-to-end process with real-time processing and cloud agility for the stream analytics and analysis and archival that you can see there. Data is streamed to the core service from Greengrass. And as mentioned previously, that can scale to billions of messages and transactions and devices. Now, the core service offers the functionality of another MQTT broker, so you can aggregate the data at Greengrass at the edge, then push it up to the IoT core service. The IoT core service has this feature called the rules engine. And the rules engine allows you to select on data that's going through the core gateway and then route that using an action to many AWS services in the back end. So as you can see, in this architecture, there's no servers that need to be installed or patched. This solution also integrates with the IoT device management, so it allows you to do bulk provision and over-the-air update of devices. Now, in this solution, an IoT rule has been set up with an action to send messages to other services, and you can see here it's setting it to Pinpoint to send messages and alerts, but also it's going to our Kinesis and Kinesis Analytics systems. The data can be persisted here as well, so you can see a data lake and an anomaly data repository. So you can have the messages being stored for use later. Now, the data that's stored in the SageMaker lake there, you can see is being accessed by SageMaker. Now, SageMaker allows you to build these machine learning models. And after you've built them, you can deploy them out to that ML models S3 bucket we see down the bottom left. And then they can be deployed those trained models out into Greengrass to run locally in your environment. And then you can use them to visualize and report and alert on possible failure at the edge. Now, what if this architecture could be simplified? As you can see, with the IoT Analytics service, this allows you to build predictive maintenance architectures that are greatly simplified. So the AWS IoT Analytics service is a fully managed service that collects, pre-processes, enriches, stores and analyzes time series data from IoT devices at scale. So in this architecture, the data collection process from machines, it goes through Greengrass the same way as before. What changes is how the data is stored, processed and analyzed in the cloud. As you can see, it's a lot simpler. The way IoT analytics works is you set up what's called a channel, and the channel then is you select the data that you want to collect, and then you can configure what's known as pipelines that can process and enrich and transform that data. The data then is after the pipeline stage, persisted in an IoT optimized data store, which is a data lake, if you like, for our time series data. So this data store is then available. You can configure what's called a data set which is, if you like, a subset of your data store, which QuickSight can then directly integrate with to create dashboards and visualizations, which is great. But you can also integrate directly with the IoT Analytics data store for SageMaker. So you can use a hosted notebook on the IoT data to do things like build predictive maintenance models. And the demo that we're going to look through, it takes a turbofan data from an aircraft engine, and then we're going to use a data set provided by NASA. And it shows you this example how you can create a hosted Jupyter notebook inside SageMaker, which can access directly the data that's been collected from your IoT devices and start to build machine learning models. I'll just switch over to the console. So when you first connect to the IoT Analytics service, you can see on the left there you've got Analyze and Prepare. Now, Prepare is to set up those channels, pipelines and data stores as a way of taking the data that's coming into the IoT core servers and collecting, doing some pre-processing and storing it so that you can make later use of it. Now, the integration with the IoT core service is done through the rules engine. So it's just another rule followed by an action to send your data to an IoT Analytics channel and ultimately down to a data store. Now, if we look at the other side here, Analyze, you can see the data sets that have been created. And a data set is a subset of a data store, which can be made available for QuickSight, for visualizations and those type of things. And then also you have this notebooks, and you can see that I've got a few set up because I've been experimenting a little bit with this great new service. If you were going to come in here later and you wanted to explore this yourself, this is available to you. When you go create, you can see that you get some templates. And the one that I'm going to step through today is this one on the right. It's the predictive maintenance on jet engines. So you can step through this yourself, which is the best way of learning, is to try it yourself. So we'll go back. I've already got this one available. As you can see, you can step through what's hosted on your notebook, and you can get through to the IoT Linux Analytics, and you can see this file. This is the notebook file, the IPYNB file. Now, I've already got this opened, and I'm not going to step through and execute all of this just because it takes a while to go through, especially training the long short-term memory neural network for this. So the way a Jupyter notebook is structured is that it's great for researchers and scientists because it allows you to incorporate code and documentation in the one place. And you can execute this code, and you can go back and execute it again and again. So at the start here, you can see it's Python code. If I highlight that, I can run that, and that'll execute that code. Now, as I said, I've already executed, so I'll step through this. You can see the outputs from when I have executed this previously, and you can try this yourself. So the way this particular model is that the business problem is that we want to predict when a turbofan is likely to fail so that we can do predictive, early maintenance on it and keep these turbofans running. Now, the first thing that you do with a lot of these Jupyter notebooks is you have to get the data in. So we've got a data set here, and we're going to use the sample data from NASA's Ames Research Center, and it represents 100 turbofan engines. We've got 21 different sensor measurements, which is shown here as S1 through to S21. And they've run it through a whole bunch of duty cycles. So you can see at which duty cycle it's expected to fail and or does fail, and then you can start to build the maintenance models on that. So this sets up some of the data structures here, imports some data. Now, this allows, this bit here incorporates the IoT Analytics service model. So what that means is that it allows the Jupyter Notebook to access the IoT Analytics service to get to your data. So you can set this up. This is some great simple code to show you how to set up so that your Jupyter Notebook hosted in SageMaker can access directly the data that's in IoT Analytics. Now, for my example, I've used the sample data set. So I don't have my own set of turbofans, unfortunately, that I can run predictive maintenance on. Maybe one day. So if you can see here, there's a little bit of logic that says if it's using the sample data set to download it from this location. So it's using a sample set in this case. But what this code shows is that, first of all, you load the data from wherever it's stored. It could be the IoT Analytics service, for the sample data here, it's loading it from that S3 bucket. And it has a look at the data here. You can see the different turbofan IDs, the sensor readings, and over a period of time. That's just the top of the data set. The code here then goes through and plots a histogram, and that's using some MATLAB libraries and that type of thing. I'll just show you the graph. Now, this has got a smooth curve on it, and you can see that on average, the engines are going to fail around cycle 206, but some fail a lot earlier and some fail a lot later. You import the data that you require into the notebook. And then we have to set up a little bit of some other attributes which are required here. Now, the one that we're going to set up is this thing called remaining useful life variable. And this is defined as the number of duty cycles remaining until the engine fails. So if you look at the code here, it's basically saying what the cycle number was at failure minus the current cycle, and that gives you the remaining useful life. And engine failure is defined as remaining useful life less than or equal to days in advance. And so we're going to use this idea of setting a number of days that we want to be able to predict in advance of it happening, so that we don't want to wait until the last day before something fails. We want to give it a bit of a heads up, if you like. And in our code here, you can see days advance. We're going to run with 30 days, so we want to know 30 days before it's likely to fail. Now, if we step through this, there's some stuff around normalizing data. So the different sensor data came from different sensors and different units. You can normalize that so you're all working from the same point of truth. And you repeat that for all the data sets. And then we go into this two different ways of training this predictive maintenance model. The first one is using logical regression. Now, just before we step into this, these machine learning models, ultimately at the end of this, you want to have a true or false, a 1 or a 0. You want to say, I need to do predictive maintenance or I don't. This machine learning model needs to give you basically one of two answers. So it's called a binary classifier. We're going to do two models, one with logical regression and one with an LTSM, which is a long short term LSTM short model. So this sets up the data to run through the model, and it predicts, it provides the outcome at the end using that data. Now, this matrix here shows, the top left shows where it got the model correctly identified an engine failure within the 30-day period. This is the false positives. The bottom left is the false negative, where it's predicted failure incorrectly. That's 127. And down the bottom there is where the model correctly predicted that an engine wouldn't fail. We'll come back to these numbers a little bit later. The second method that this notebook uses is to create these predictive maintenance models is called the long short-term memory approach. Now, this is a lot more of an iterative approach. It incorporates things like memory. It's great for IoT use cases. You need to use a bit of a random number generator here, and I'll explain why you use that random number a little bit later. You set up some data structures, setting them up there. Some more setup of the model itself. And then it runs through the model and it does what's called an epoch. Now, the way this works is that it takes your test, your training data, and it carves off a percentage of that for, if you like, testing. So in this example, it's covering 5% for testing, and the random number generated sort of randomizes what 5% that is. So you can see it goes through multiple epochs here, and it goes through up to 25 epochs. Now, each epoch is an iteration through the machine learning model, and at the end of it, it tests the accuracy of what it's done against the random 5% that it's, if you liked, put aside for testing. Now, if you can see the accuracy in this column here, 92%, 92.41, and as you can see, after each epoch, it's gradually increasing. And you can find with these types of iterative models that they start to plateau after a while, or sometimes even bounce around and reach a point where further iterations aren't beneficial. And we can actually plot this on a graph. It's great to visualize this. So the training data that's being used is the blue one, and as you can see, that's the one where it carves off 5% after each epoch. And you can see that the validation data is following that as well, so that you can see that you can start to model how many iterations and the type of parameters you need in the model to efficiently get to a useful model. And there's a little bit of cleanup here, and there's a little bit of other work. You can see it creates a similar matrix here on the false positives and you know, the accuracy of the system. It applies, there's some test data with this one, and it applies the test data to it, and you can see the resultant accuracy. So this is test data that's outside of the training data, not the stuff that's carved off. It's a separate data set. And in summary, it looks at these two different models, the logical regression model and the LSTM metrics. And you can see the accuracy is pretty similar. It's interesting that the document says the logical regression has a higher accuracy and recall, but when I ran it, the random elements, the LSTM, came out slightly accurate. And the precision and recall are interesting to consider in this. So it depends what your use case is. So if you care more about your model predicting faulty devices, then precision is more important. And as you can see in this case, you'd use the LSTM approach. However, if you were just making sure, you know, if you were modeled to show all possible devices that could fail, so, you know, you're looking for a lot wider set, then recall would be a more important thing. And logical regression might be, well, it shows here it's a better model for that. And also it requires less processing than the LSTM one. So once you've built and trained these models in SageMaker, you can deploy them out to create that deployed model and deploy it to an S3 bucket and make it available. Now you can deploy that model then down to Greengrass to run locally. Now this actually in the notebook runs the deployment in the cloud. So you can see it running. It actually runs through a particular engine, 31, and it steps through the duty cycles for the different models. And then you can see the binary classifier, so it's 0. And then you can see at which point the different models and reality predict when things are going to fail. And as you can see, it's, at least in this case, it has provided something that is quite useful. So I hope stepping through that has assisted in seeing how you can use SageMaker and IoT Analytics to take IoT data and build these models, and then you can deploy them both in the cloud, but also deploy them back to Greengrass to have local detection of these events. And we've got some customers that are doing just that. So we've got a customer that builds pumps, and their devices are running FreeRTOS, which is our microcontroller operating system. And that data that those devices are collecting is sent directly to a Greengrass-enabled device locally. The Greengrass-enabled device is running the predictive model that they've built to identify when vibrations are at a level that is important to understand and detect and do maintenance on. When internet connectivity is available, it sends all the data that it's collected to the cloud, the relevant data to the cloud, so you can improve your models. So there's two really important key points there. First of all, Greengrass locally will keep running as set up if there's not an internet connection, so you're not dependent on your internet connection in this environment. And the second point I want to make is that it's an iterative process, this predictive maintenance. You deploy your models, and then you run them in production, and you validate that they work in real use cases. And then you collect more data to go back and improve the model over time. There's an iterative loop that you can deploy, building and training models on the cloud using SageMaker, and deploying them down to Greengrass to run locally. And you can get, you want to get your models as close to 100% accurate as possible. Another customer that's doing great work with predictive maintenance is Stanley Black & Decker. So they're using similar services to understand when their devices are going to fail. So they're using edge-based application in Greengrass. They're looking for known signatures, especially their high-value tools, to indicate when these are going to fail. And it's generated a range of benefits for Stanley Black & Decker around fuel savings and improved efficiency of their technicians, etc. Another company that's doing some great work with predictive maintenance is Wärtsilä, and I apologise if I pronounced that incorrectly. They've got an interesting solution in that they've got marine engines that they want to understand when they need to service. So they've got 14,000 ships out with 35,000 engines installed. Now, we worked as part of a team with Accenture and with some account SAs and Salesforce SAs to build this solution where they could do predictive maintenance on their engines. Obviously, it's a need to keep the ships at sea. Interesting point to consider with this solution is that the boats a lot of the times will be out in the ocean and have poor internet connectivity. So the solution needs to collect all the data as it's collected in operation, but then when ships are back at dock, be able to upload that data to the cloud so you can build and trade better predictive maintenance solutions. And those predictive maintenance solutions also need to run on the ships so that you can predict if something's going to fail early. So it needs to run when there isn't internet connectivity, so you need to run that locally on the device. I've talked a little bit about predictive, crazy with these buttons, sorry. I've talked a little bit about predictive maintenance. I wanted to dive into predictive quality as well. Now, it's a similar architecture and similar patterns, but it's also a use case that we're seeing a lot of industrial IoT customers make use of. So, for example, Kempe use AWS to bring its IoT solution for its welding machines to market. And it cuts the cost of the software development by about half. Now, this software lets an operator automatically apply parameters that have been stored in the cloud, and it makes the devices easier for them to use. And it authenticates users so they only work on tasks they're qualified for, and it saves information about every weld so that you can improve their environment over time. And a predictive quality architecture will look like this. Now, this might look a little bit similar to the first predictive maintenance one that we showed. A couple of things that I wanted to talk to that are additional and perhaps didn't talk about earlier. First of all, you can see a snowball near the bottom right there. Now, a snowball is a device which we can send to you when you need to move terabytes of data to the cloud. So you can request these in the console and we'll send them to you, connect them to your network, you load the data on, and then you ship the data back to us, because in this instance of terabytes of data, it's more efficient to move the data to the cloud that way. The new version of the Snowball Edge, actually comes with some local compute. So you can take Lambda functions you've authored in the cloud and deploy down to Snowball Edge. So you can do pre-processing of data on the edge. And also we've recently launched the SBE1 instance type. So this is instances which you can create in the cloud, server instances, You can save them as an Amazon machine image, and then you can deploy them to run in these Snowball appliances. And what that means is that if, for example, you're in a remote location like a boat at sea or say an airliner, and you want to collect a lot of data and process it and normalize it and prepare it locally, you can take Lambda functions and EC2 instances that you've created and deploy them to run locally before you send the data to the cloud. So that's option 2. That's one thing I wanted to point out. The other thing to note on this slide is the vision bit. So down the bottom, you see bottom left, you can see vision. And one of the things about quality control is that you can incorporate things like cameras and LiDAR and 3D cameras. You can incorporate that visual data, load it up into S3, and you can start to build machine learning models that incorporate image classification techniques, for example, to create great solutions. So you can build models around understanding what's happening in your environment. So I actually worked in Australia with a local partner who's built something around safety for factories. So they're using image classification techniques on existing cameras to understand when vehicles and people are in shot, in the camera shot. And also they then apply another model that tracks where they're moving. And then they use another machine learning model that predicts where they're likely to go based on previous behavior. And based on this ability to identify vehicles, track them and predict where they're going, and then identify people and track and predict where they're going to go, they can raise alerts if there's likely to be an accident. And they've built machine learning models. They've got this running in a range of facilities in Australia now. And that's, safety is critical to the quality of your environment as well. Now, this is a solution, as you can see, it's very similar to the predictive maintenance. And if we use the IoT Analytics service, you can see again, it really simplifies the environment. The main things that are different here is that you've got the ability to incorporate these visual environments, these camera systems and even audio systems, and start to run analytics on the data to increase the predictive quality of your environment. So what sets AWS Industrial IoT apart? So interoperability, because you can use the same software development lifecycle and cloud computing, cloud development models that you used to, and author Lambda functions using Python, Node, and Java in the cloud, but then deploy them to run locally. You have the ability to control the logic across your entire environment from the factory floor right into the cloud. You can use our shadow services at the edge in the cloud too, so that allows you to understand the state of things and set and get them at any point in time. You can run decentralized architectures because AWS IoT is available in many regions around the globe. You can do real-time capabilities because Greengrass can extend the functions of AWS IoT into your environment, so you get these low latency response for really mission critical industrial use cases. Now, because you can author Lambda codes to the edge and Greengrass allows that integration with the cloud, you can also make use of all of our 100 plus services in the cloud around analytics or creating workflows or machine learning, for example. And an important thing to understand too is around this machine learning model that we've created not only, if you like, a complete model for deploying software out to the edge using cloud development techniques, but you can do machine learning model creation, the build, train and deploy those models in the cloud for the build and train, but then deploy them either in the cloud or down to the edge. Security is key to these environments and it's job zero at AWS. All communications are encrypted using TLS and mutual authentication. We've introduced the IoT Device Defender service, which secures your fleet and audits policies and looks for anomalies and those type of things. And lastly, we've got the IoT Analytics service, which really simplifies the process of collecting IoT data so that you can, and the integration with services like SageMaker and Greengrass really makes it easy for you to build and train these predictive maintenance models. And more importantly, by making it easier, it allows you to iterate quicker and then arrive at better solutions quickly. Our IoT services, we launched IoT Core in 2015, and that's the cloud-based service which allows you to securely connect devices to the cloud and to other devices. We launched Greengrass a little bit later, and that's our edge service, which extends that capability down to the edge. As I mentioned, that will run on virtually any type of CPU run device. Amazon FreeRTOS is our microcontroller operating system, which allows low-powered devices to connect into Greengrass and into the cloud. And as you can see, we also have device management, which supports the bulk onloading of lots of devices, allows you really easy to search and index on those devices and run jobs like configuration updates and software updates from the cloud. Device Defender, which is around securing your IoT environment and alerting on anomalies and misconfigurations. And then, of course, the IoT Analytics service, which we've dived into today. One question customers ask is, when do I use Greengrass and when do I use the IoT service? So we tend to think of these three laws or dimensions when we're making that decision. So if you're thinking about doing processing at the edge or in the cloud, you might want to consider the law of physics. So if you need a low latency response to some sort of a logical function, you want to have that running at the edge, so low latency. Also, if you're in a disconnected or a poorly connected or a remote area, that might drive you to do edge processing as well. So that's the law of physics. The law of economics, we're collecting more and more data, and it's getting harder and harder to move around. So it can be quite expensive, especially to send visual data or audio data to the cloud. So in many cases, it makes sense to process the data locally and only send relevant data to the cloud. And when you're doing machine learning modeling and researching, the sooner you can prepare your data into a form that can build these models, the better, because that could typically take 80% of the time. So taking those three laws together, you can make a decision around whether you want to do edge processing or do the processing in the cloud. And Greengrass has quite a few features, an expanding set of features. You can, it acts as a local broker, so you can have messages locally communicating with devices communicating to the Greengrass core, but they're also via that to other local devices, so you can have like a local message broker. You can also send those messages to the cloud. You can have Lambda functions triggered on those local actions. You can make use of our shadow service. So if you're a cloud developer and you need to talk to or integrate with the state of devices, you can use the shadow service to that, where we handle the disconnects and the reconnects. Devices typically can be disconnected for a period of time because of power and network outages. So it's a great service to simplify development. Security, it's AWS grade security. As I've mentioned previously, everything's mutually authenticated certificates and encrypted in transit. Local resource access is interesting. So if you've got a local device that is connected to your Greengrass gateway, you can securely provide read or read-write access to individual Lambda functions. So if you have a particular, say, interface which has a protocol that needs to be converted, or you have a particular type of camera device in your industrial application that you want to provide access to a Lambda function, that's available. Machine learning, which we've talked a lot about, which is around taking models you've trained in the cloud and having them run at the edge. Protocol adapters, that's to make it easy for people to take legacy protocols and industrial protocols and convert them to internet protocols so that you can get your data to the cloud. And all of this is supported on the Greengrass core, which is, if you like, the runtime software that Greengrass is deployed with, and that can be updated over the air at any time so that you're always at the latest version for performance, security and features, etc. And this is a bit of an eye chart, and we've talked about a lot of the services on the left two sides there, but the reason I want to point this is that a lot of people are building IoT solutions. They make use of all of our services, and we've got the broadest and deepest set of services in the cloud. And this makes it easy for people to build end-to-end solutions, not just around their industrial applications, but making that data available for enterprise applications as well by using other services upstream, if you like. And being first in the cloud has also allowed us to build the broadest, largest partner ecosystem. So we've got partners who can build solutions, come in and assist you, like our consulting and SI partners. We've got partners like C3 IoT and Splunk who can provide a hosted platform that can perform some of these functions. You can make use of that as well. And they've got some great solutions for predictive maintenance as well. Connectivity solutions, in many cases there are remote networks, constraints around geography and those type of things. So we've got a large range of connectivity partners, and then we've got hardware manufacturers as well that can deploy hardware both for sensors and also for green grass enabled gateways and edge devices out into your environment. So thanks for listening today. I hope you've learned a little bit about predictive maintenance and how you can use AWS IoT and our AWS IoT Analytics service and SageMaker and Greengrass to build great predictive maintenance solutions. If you'd like to learn more, we've got a couple of links here, and that'll allow you to download a couple of ebooks which go into a little bit more depth on these solutions, and then reach out to your account team if you'd like to know more about how you can use AWS IoT. With that, let's do some Q&A.